All right, let's talk about something we all deal with every single day, the roads we drive on. We're going to peel back the asphalt and look at the hidden science that decides whether your commute is smooth or, well, not so smooth.
You know the feeling, right? You're cruising along, everything's fine, and then bam! For the next mile or so, it feels like you're driving on a washboard. And then, just as suddenly as it started, it's perfectly smooth again. What is the deal with that?
Well, I can tell you it's not a mistake. It's not just random wear and tear. That sudden change is actually the result of a very deliberate, data-driven system working completely behind the scenes. And that's what we're going to get into.
See, to solve this huge puzzle of maintaining our roads, engineers can't just run around fixing potholes as they pop up. No, they need a bigger strategy, a kind of master plan for the whole network.
And that master plan has a name, Pavement Asset Management. The best way to think about it is like a detective agency for our roads. Its whole job is to constantly keep an eye on the health of every single street and highway, figuring out where to spend time and money most effectively.
And just like any good detective, this system needs clues, a ton of them. We're talking about the obvious stuff you can see, like cracks and the bumpiness you feel, but it goes way deeper, measuring things you'd never notice, like the grip of the road, its hidden structural strength, and even digging into its construction history. All of this builds a complete case file for every single stretch of pavement.
Okay, but collecting all that data is just one piece of the puzzle. The real magic, the real breakthrough, happens when they figure out how to organize it all. And that brings us to what is probably the most important clue in this whole investigation.
So here's the secret. You can't just look at a 20-mile highway as one single thing. It's just too big, too varied. The key is to break it down into smaller, more manageable pieces where everything is basically the same.
And that piece has a name. It's called a homogeneous section. It's just a stretch of road that tells the same story, you know? It's got the same kind of pavement, handles the same amount of traffic, and has the same level of wear and tear. This little section becomes the fundamental building block for every single repair decision they make.
And why on earth do they go to all this trouble? Because it literally changes the entire game. Once you start thinking section by section, your decisions get way smarter. Your predictions for when a road might fail become incredibly accurate. You can pick the perfect treatment for one specific part of the road, which, at the end of the day, means your tax dollars are being spent way more efficiently.
Now, it turns out there's even a bit of a debate about how to define these sections. Some folks like fixed sections, where the boundaries are set in stone, making them super easy to track over time. Others go for a dynamic approach, where they redraw the lines every year with the latest data for pinpoint accuracy. And of course, some try for the best of both worlds. It just goes to show you, even in road science, there's always more than one way to crack a case.
So if breaking a road into these sections is so important, how do you know exactly where one section stops and the next one begins? Well, for that, our road detectives have to bring out their high-tech forensic tools.
The mission is simple. Find the exact spot where the road story changes. Where does it switch from smooth to bumpy, or from light traffic to heavy? In the world of statistics, there's a name for this whole process. It's called change point analysis.
And one of the most powerful tools in their kit for finding these spots is a statistical method with a kind of cool name. It's called QSUM, which is short for cumulative sum.
So how in the world does a math formula find the exact physical point on a highway where things get worse? How does that even work?
It's actually really clever and pretty simple in concept. Think of it like this. First, a special vehicle drives the road and measures its roughness at thousands of different points. Second, the computer compares each one of those points to the road's overall average roughness. Third, it starts keeping a running tally of the differences. So if the road is smoother than average, the total goes down. If it's rougher, the total starts to climb. And that leads to the big finale.
When you plot that running total on a graph, the exact point where the line suddenly changes direction, say it stops going down and starts shooting up, that's it. That's your change point. It's like a giant statistical red flag telling the engineers, hey, pay attention, something is fundamentally different right here.
Now, of course, QSUM isn't the only tool they use. Any good detective has a whole bag of tricks. They use a bunch of other advanced statistical methods to double-check and triple-check their work, so they can be really confident they found the exact spot.
Okay, let's put it all together. We've got our detectives, we've got the clues, we've got the forensic tools, so what's the final verdict? What does this all add up to?
Well, the stakes are unbelievably high. The research is crystal clear on this. If you mess up the sections, you will absolutely use the wrong fix at the wrong time, and you'll end up wasting a ton of money.
But
When you get it right, that's the huge payoff. The perfect treatment gets applied to the perfect section of road. A part that needs a whole new surface gets one, while the section right next to it, which only needs a few cracks sealed, gets just that. Resources are used with surgical precision, which means our roads end up being safer, they last longer, and we all save a lot of money in the long run.
So the next time you're driving and you feel that road suddenly change under your tires, you'll know why. It's not random. It's a boundary, a change point discovered by science and data. And it really makes you wonder, doesn't it? What other parts of our world are being shaped by these invisible streams of data that we never even get to see? Thanks for diving into this with me.